One of the standard ways of working with networks is to determine or assign specific types of structures to the network, and that gives us a way of analyzing it and exploiting that structure to prove other properties. One fundamental subclass of networks is called a tree, and a tree is, in its simplest form, is an undirected network that is all connected together and has no cycles. And so we're starting to see some terminology that we haven't really come across yet, but we can understand it still in kind of a lay, just kind of based on English, rather than relying on a crisp definition, which is something that we'll get to in about a week or so. So connected really just means that if we follow the edges, we can move from any node to any other node by essentially a sequence of edges. And cycles means that there's no cycle. So that means that there's no essentially orbit where we can go from one node, follow the edges, and come back to the same node. So there are no cycles, but everything is still connected together. So there's not some sort of disconnected node just sitting out here, that everything must have an edge to it. And so one of the implications of having no cycles is that there is only one way to get from each node, between every pair of nodes, essentially. So if I were to pick two nodes here, this one and this one, there's only one way to get there. In order to make two ways to get there, if I added an edge here, that would actually create a cycle, which would be this cycle here. If we have a collection of trees, this constructs what's called a forest. Network scientists are sometimes humorous in their definition of terms. So the forest is essentially just a bunch of trees that aren't overlapping with each other. And so if we wanted to be very precise about that, we'd call that a disjoint union, which means that there isn't any sort of overlapping. One of the important things about trees is when you start to do visualization of them, there's many different ways to look at a tree. And so while this may make a lot of sense based on what we've talked about a tree, these two networks are actually exactly the same. So if you were to pick this node up and move it up to the top and shift everything around, you'd see that they're actually the same tree. We've just visualized it differently. And this one is an example of a rooted tree in the sense that there's this beginning root, and then everything comes out of that. One of the reasons why trees are important is because they represent a number of important structures like family history, like a social hierarchy, and they also have some very strong structure which allows us to have some very strong properties about it. One of the other things that you can see is that just because it's not drawn like this doesn't mean that it's not a tree. This one right here is also a tree, and if you wanted to root it, you could actually root it from just about any node. You could maybe pick this one to root it, but just as well you could pick one of these, or you could even pick this node to root it and draw everything else relative. So it really depends on what the nodes are relative to the rest of the system. So now I'd like to use a tree as a vehicle to show you what a proof could look like in the context of a graph or a network, just to start to see how we might prove things and understand things in a slightly more rigorous fashion. So the statement we're going to prove is that a connected graph, G, with n nodes is a tree if and only if it has n minus 1 edges. And so this if and only if, this is a construction for those of you that haven't had a lot of proof-oriented mathematics, is the fact that that's an exact condition. So that means that the graph being a tree is exactly equivalent to having n minus 1 edges when it has n nodes. So if it's an n node tree, that's exactly the same as having a graph that has n nodes and n minus 1 edges. And one important thing that I didn't mention in the proof in the statement of the theorem here is the fact that it's going to be finite. So we have to have a finite tree or finite network, but that's pretty self-explanatory. So when we prove an exact condition, we need to prove it in both directions. So that means we suppose that it is a tree, and our job is to prove that it has n-1 edges. Then we go the other way and say, suppose it has n nodes and n-1 edges, and we need to prove that it is actually a tree. So that's going both directions. So going in the forward direction, we suppose that G is a tree, and we're going to prove this direction using induction. And induction is this method of essentially building our example from essentially unit size up to full size. And so if we have a single node, then n is equal to 1, and we don't have any edges. And so the number of edges is n-1, which would just be 0. So this satisfies this theorem. So it says that it is a tree, and it has n-1 edges. So it is true for this very lame version of a tree. And so now the way that induction works is that we assume, once we prove it for this initial case, we assume that it is true for the n case, and then we try to prove it for the n+1 case. So if we suppose that this theorem is indeed true for n nodes, so G is a network that has n nodes and n-1 edges, and it is a tree. And so we're now going to add one node and observe what happens to the edges. And so if we are looking for a tree, we need to make a tree with n-1 nodes. Then what we're going to do is we're going to add one node to this existing graph G, which we already know is a tree. And so by this black circle here, I'm denoting the bounds of what we are going to call G. And so these are two nodes inside of G, and it could be any two nodes. And this is our new node that we're going to be adding, the n+1 node. And so if we don't add either of these blue edges, then it's disconnected. And so if we don't have either of these blue edges, then this new node is disconnected, and so it doesn't satisfy the fact that a tree needs to be connected. So we can't just have 0 edges added. If we add more than one edge, so if we add 2 or more, then what ends up happening is, so let's take a look at the case where we add 2 edges. We add one edge to one node that's already in G, and we add another edge to another node that's in G. And because G is already a tree, we know that there exists some path in the graph to get from this node, let's call U, to this node, which we'll call V. So there already is some path to get to U to V, and now we've added these two new blue edges, which creates a cycle, and that contradicts the definition of a tree. So if we had any more than 2 edges, we'd have the same problem. We just may have it even more. We may make even more cycles. So what that means is we can't have 0 edges to make it a tree, and we can't have more than 1 edge to have a tree. So we must have exactly 1 edge added, and which means that the number of edges, so in this case the number of edges, is going to be n-1, which is what we add here, plus 1, which would just be n. And so this, we have n edges and we have n+1 nodes, and so that means that this theorem is indeed still true. Going now in the reverse direction, we're now going to assume that we have a graph with n nodes and has n-1 edges, and we're trying to prove that it is a tree. All right, so if we suppose that G has n-1 edges, so if it is already a tree, then we're done and we finish. If it's not a tree, if we're going to claim that it's not a tree, then it must contain a cycle inside the graph. And so what we're going to do is we're going to pick an edge in that cycle and we're going to delete it. And we're going to do that until we no longer have any cycles, which means that we're going to have a tree once we delete all the edges that form those cycles. And if we call the graph that remains, this G tilde, that has to be a tree. And by virtue of the previous slide, we can say that that tree needs to have n-1 edges. So if we started, if G has n-1 edges, and then we removed what constituted the edges that constituted the cycle to leave us with n-1 edges, that's actually a bit of a contradiction, because we start with n-1 edges, we end with n-1 edges, and we said we removed some things in between. So because n-1 and n-1 are exactly the same quantity, that means that we couldn't have removed anything, which means that this option right here cannot be true. So that means that this is not true, and so that means that indeed this first condition must be true, that it is a tree. So if G is a graph that has n nodes and it has n-1 edges, then it is automatically a tree. And so that shows you kind of using two different ways, a contradiction here and using induction in the forward direction. We showed this theorem that a connected graph G with n nodes is in fact a tree if and only if it has n-1 edges.